Nanomaterials are simply materials that have at least one dimension in the range of 1 to 100 nanometers. Think of a grain of sand that is about 1 millimeter wide. A nanomaterial would be a grain 1,000 times smaller, about the size of a virus. Classification: zero-dimensional, 0D particles, quantum dots, nanocubes. All three dimensions are confined. Example: a 5 nanometer gold nanoparticle behaves differently from bulk gold. One-dimensional, 1D nanowires, nanotubes, nanorods. Two dimensions are large. One is confined, for example a carbon nanotube with a diameter of 1 nanometer and length of 10 micrometers. Two-dimensional, 2D nanosheets, graphene, molybdenum disulfide. One dimension is confined, the other two are extended like a leaf. Three-dimensional, 3D nanostructured, porous foams. Nanocomposites where nanoscale building blocks fill a bulk volume. Fundamental properties that change at the nanoscale include: surface-to-volume ratio. Surface atoms increase dramatically, giving higher reactivity, like a cake with more frosting. For a sphere, surface area equals 4 pi r squared and volume V equals 4/3 pi r cubed. The ratio A over V equals 3 over r grows as radius shrinks. Melting point depression. Smaller particles melt at lower temperatures because surface atoms are less tightly bound. Optical properties. Nanoparticles can absorb and emit light at specific wavelengths. For example, quantum dots glowing different colors. Mechanical strength. Nanocrystalline metals often become harder because grain boundaries hinder dislocation motion. These shifts arise from the same underlying reason. When you shrink a material, the proportion of atoms that sit at or near a surface or interface grows, and the rules that apply to an infinite crystal no longer dominate. When a material's size becomes comparable to the wavelength of an electron, its de Broglie wavelength, the electron's motion becomes quantum confined. Imagine a guitar string. A long string can vibrate in many ways, low-frequency notes, but a very short string can only vibrate at a few high-frequency notes. Similarly, electrons in a nanoparticle can only occupy discrete energy levels. Consider an electron confined in a one-dimensional box of length L. The Schrödinger equation gives psi n of x equals square root of 2 over L times sine of n pi x over L. N equals 1, 2, 3, and so on. The allowed energy levels are E sub n equals n squared h squared divided by 8mL squared. As L shrinks, the spacing between E sub n grows proportional to 1 over L squared. This explains why a 2 nanometer CDC quantum dot absorbs blue light, while a 5 nanometer dot absorbs red light. For a semiconductor nanoparticle, the band gap increase delta E sub g can be approximated by the Bruce equation. Delta E sub g of r equals h bar squared pi squared over 2r squared times the quantity 1 over m e star plus 1 over m h star minus 1.8 e squared divided by 4 pi epsilon naught epsilon rr. The first term, kinetic energy, dominates for very small r, making the gap larger, a direct reason why nanosilicon can glow. Other physical properties. Magnetic susceptibility. In ultra-small ferromagnetic particles, superparamagnetism appears because a single domain can flip its magnetization thermally. Heat capacity. At the nanoscale, phonon modes are limited, causing deviations from the Bulk-Dulong-Petit law. All these effects are rooted in the confinement of electrons, phonons or magnons within a dimension comparable to their characteristic wavelength. Carbon nanotubes, CNTS, are long, thin cylinders made of graphene sheets rolled up. Three main laboratory methods produce them, each resembling a different kitchen technique. Arc discharge, like striking a spark between two carbon electrodes in an inert gas. A high current, approximately 100 amperes, creates a hot plasma, approximately 4,000 Kelvin, that vaporizes carbon. As the vapor cools, carbon condenses into tubular structures on the walls of the chamber. Advantages: produces relatively high-quality multi-walled carbon nanotubes, MWCNTS, and some single-walled carbon nanotubes, SWCNTS. Drawbacks: mixture of byproducts, low yield, and the need for a graphite anode. Laser ablation. Imagine a powerful laser beam, ND:YAG 1064 nanometers, pulsing onto a carbon target containing a catalyst, often nickel or cobalt. The laser ejects a plume of carbon atoms and clusters. When the plume expands into a heated furnace approximately 1,200 degrees Celsius, with a flow of inert gas, the carbon reassembles into nanotubes. This method gives high-purity SWC/NTS with narrow diameter distribution, but the equipment is expensive and the material cost is high. Chemical vapor deposition, CVD, the most scalable method, comparable to baking a cake. A substrate, silicon wafer, quartz, or metal foil, coated with a thin catalyst film, iron, cobalt, nickel, is heated to 600 to 900 degrees Celsius. A carbon-containing gas, CH4, C2H2, C2H4, flows over the hot catalyst. The gas decomposes and carbon atoms dissolve into the metal particles, then precipitate out, forming a tube that lifts off the particle. Thermal CVD, heat only. Plasma-enhanced CVD, PECVD, plasma provides extra energy, allowing lower temperatures. Alcohol CVD uses ethanol as a milder carbon source, reducing amorphous carbon. CVD can grow vertically aligned arrays, forests, or individual tubes with controlled length and orientation, making it the workhorse for industry. A carbon nanotube can be thought of as a sheet of chicken wire, graphene, rolled into a tube. The way you roll it, its angle and direction, determines its chirality, which in turn decides whether the tube behaves like a metal or a semiconductor. Indices N(m). The graphene lattice is described by two basis vectors, a 1 and a 2. Rolling the sheet so that the vector CH equals N, a 1 plus M, a 2 joins together creates the tube. The pair N(m) are called the chiral indices. Armchair tubes, N equals M. The rolling direction looks like the armrests of a chair. These tubes are always metallic. Zigzag tubes, M equals 0. The edge looks like a zigzag pattern. They are metallic when N is a multiple of 3, otherwise semiconducting. Chiral tubes, any other N(m), their properties vary continuously between metallic and semiconducting. Diameter, D equals a divided by pi times the square root of N squared plus Nm plus M squared, where A equals 0.246 nanometers is the graphene lattice constant. For example, a 10,10 armchair tube has D approximately 1.36 nanometers. The structural types: single-walled carbon nanotubes, SWC/NTS, 1 graphene layer, diameter 0.5 to 3 nanometers, length up to many centimeters. High aspect ratio, length over diameter greater than 10 to the 4. Multi-walled carbon nanotubes, MWC/NTS, several concentric tubes, 2 to 100 walls. Outer diameters 5 to 100 nanometers, inner diameters can be a few nanometers, like a Russian nest doll of tubes. The number of walls and spacing, approximately 0.34 nanometers, same as interlayer distance in graphite, affect mechanical stiffness and thermal conductance. Understanding chirality lets engineers select the right CNT for a given task: metallic for interconnects, semiconducting for transistors, or specific diameters for reinforcement in composites. Mechanical performance. Young's modulus, E, for an ideal single-walled carbon nanotube continuum mechanics predicts E approximately equal to Y divided by a wall, approximately 1 terapascal. Y equals 340 gigapascals, the in-plane stiffness of graphene, and a wall equals 2 pi RT, the effective wall area with T approximately 0.34 nanometers. Experimental values range from 0.5 to 1.0 terapascals, comparable to steel, about 200 gigapascals, but at a fraction of the weight. Tensile strength, the theoretical fracture stress is about 100 gigapascals. Real carbon nanotube fibers achieve 3 to 10 gigapascals, still 10 to 20 times stronger than steel on a weight basis. Aspect ratio, length divided by diameter can exceed 10 to the power 4, enabling load transfer over long distances when embedded in polymers. Electrical conductivity. For a metallic armchair carbon nanotube, the conductance per tube at room temperature is G equal to 2E squared divided by H, approximately 77.5 microsiemens, corresponding to a resistance of about 12.9 kilo ohms per tube. Bundles of many tubes lower the overall resistance dramatically. G equals 2E squared over H, approximately 77.5 microsiemens. Mean free path, L, can be several micrometers, far larger than in copper, about 40 nanometers. Hence, current densities up to 10 to the 9th amperes per square centimeter are tolerated, orders of magnitude higher than in conventional metals. Semiconducting carbon nanotubes exhibit a band gap, for example, approximately equal to 2 gamma naught times a divided by d, where gamma naught is about 2.9 electron volts and d is the diameter. This size-dependent gap enables transistor action. Thermal conductivity. Phonon transport dominates. The intrinsic thermal conductivity of a pristine single-walled carbon nanotube can reach kappa approximately 3,000 watts per meter Kelvin along the tube axis, surpassing diamond about 2,000 watts per meter Kelvin. Kappa equals 1/3 times CV times Vg times L, where CV is specific heat, Vg the group velocity, about 2 times 10 to the 4th meters per second, and L the phonon mean free path, up to a micrometer. Defects, tube-to-tube contacts, and bundling reduce kappa to a few hundred watts per meter Kelvin in realistic composites. Overall, carbon nanotubes offer a unique combination. Stiffness like a steel rod, strength of spider silk, electrical highways for electrons, and thermal superhighways for heat, all at nanometer scale. The surface of a carbon nanotube is made of sp2 bonded carbon atoms, similar to graphene, which means it is chemically inert to many reagents. However, by functionalizing the surface, we can attach other molecules, change solubility, and tailor properties. Types of functionalization. Covalent functionalization directly forms new bonds with the carbon lattice, for example, oxidation to create carboxyl groups, fluorination, or cycloaddition reactions. This disrupts the pi system, decreasing electrical conductivity, approximately 10 to 30% loss, but dramatically improves dispersion in water or polymers. Example, treating CNTS with a mixture of H2SO4/HNO3 creates carboxyl groups, turning a black powder into a brown slurry that can be mixed with epoxy. Non-covalent pi-pi functionalization uses surfactants, polymers, or aromatic molecules that wrap around the tube via van der Waals forces, preserving the electronic structure. Example, sodium dodecyl sulfate, SDS, micelles or DN, strands can solubilize CNTS in aqueous media without breaking the conjugated network. End cap functionalization reactions at the tube ends, which have higher curvature and more reactive sites, allow attachment of catalyst particles or linking groups for network formation. Impact on properties. Solubility and processability. Functional groups make CNTS hydrophilic, enabling inkjet printing or spin coating for electronics. Mechanical reinforcement. Covalent bonds between CNTS and polymer matrices improve load transfer, raising composite strength by up to 30%. Electrical tuning. Non-covalent wrapping with electron-donating polymers can shift the Fermi level, converting a semiconducting tube to a metallic-like behavior. Thermal interface. Surface groups can improve thermal contact resistance when CNTS are used as heat spreaders. Designing the right functionalization is a trade-off. Preserve the intrinsic properties, keep the lattice intact, while achieving the needed compatibility with surrounding materials. Characterizing carbon nanotubes requires tools that can see at the nanometer scale, and also probe their chemical and physical behavior. Transmission electron microscopy, TEM, direct imaging of inner walls, defects, diameter, number of walls. Determining N(m) indices by diffraction patterns, measuring wall spacing approximately 0.34 nanometers. Scanning electron microscopy, SEM, surface morphology, alignment, bundle formation, length micrometers to centimeters. Quick inspection of carbon nanotube forests, quality of growth, and electrode integration. Raman spectroscopy, vibrational modes. G-band graphitic, D-band defects, radial breathing mode, RBM frequency, omega RBM approximately 248 divided by D nanometers gives diameter. D/G intensity ratio indicates defect density. X-ray diffraction, XRD, crystallographic spacing, wall spacing, degree of graphitization. Detecting the 002 graphite peak approximately 26 degrees 2 theta and estimating number of walls. Atomic force microscopy, FM, topography, height diameter, mechanical force measurements. Measuring the height of individual single-walled carbon nanotubes on a substrate approximately 1 to 2 nanometers and mapping adhesive forces. Electrical measurements, 4-probe conductivity, IV characteristics, contact resistance. distinguishing metallic versus semiconducting tubes, extracting mobility. Thermal conductivity, laser flash 3 omega heat transport along tube axis, assessing intrinsic kappa and effective functionalization. Practical workflow often starts with SEM to locate carbon nanotubes, moves to TEM for detailed wall count, then Raman to quickly assess quality, and finishes with electrical and thermal tests for device applications. A single-walled carbon nanotube has a diameter of 1.2 nanometers and a length of 2 millimeters. Compute its aspect ratio, L/D, and comment on its significance for reinforcement. Convert units. L equals 2 millimeters equals 2 times 10 to the 6 nanometers. Aspect ratio, R equals L divided by D, equals 2 times 10 to the 6 nanometers, divided by 1.2 nanometers, approximately equals 1.67 times 10 to the 6. An aspect ratio greater than 10 to the 4 means the tube can bridge many polymer chains, delivering efficient load transfer and high-strength enhancement. A bundle contains 10 to the 9 identical single-walled carbon nanotubes, each of length 1 micrometer and diameter 2 nanometers. Estimate the total external surface area assuming the tubes are closely packed, ignoring interior walls. Express the answer in square meters. Surface area of one tube. A subtube equals pi dl equals pi times 2 times 10 to the minus 9 meters times 1 times 10 to the minus 6 meters, approximately equals 6.28 times 10 to the minus 15 square meters. Total area. A subtotal equals 10 to the 9 times 6.28 times 10 to the minus 15 square meters equals 6.28 times 10 to the minus 6 square meters. Convert to square centimeters. 6.28 times 10 to the minus 6 square meters equals 6.28 times 10 to the minus 2 square centimeters. Though the absolute number looks tiny, the specific surface area per gram can reach greater than 1,000 square meters per gram for dispersed carbon nanotube powders. A polymer matrix, tensile strength 50 megapascals, is reinforced with 0.5 weight% single-walled carbon nanotubes that have an intrinsic tensile strength of 100 gigapascals and Young's modulus 1 terapascal. Using the rule of mixtures for strength sigma sub C equals Vf sigma sub F plus Vm sigma sub M, estimate the composite strength. Assume densities. Polymer 1.2 grams per cubic centimeter, carbon nanotube 2.1 grams per cubic centimeter. Convert weight fraction to volume fraction. W sub F equals 0.005. Mass of carbon nanotube per 1 gram composite equals 0.005 grams. Polymer equals 0.995 grams. Volumes, V sub F equals mass sub F divided by rho sub F, over mass sub F divided by rho sub F plus mass sub M divided by rho sub M, equals 0.005 divided by 2.1 over 0.005 divided by 2.1 plus 0.995 divided by 1.2, approximately equals 0.00286, approximately 0.29%. Volume fraction of matrix V sub M equals 1 minus V sub F, approximately equals 0.9971. Apply rule of mixtures. Sigma sub C equals Vf sigma sub F plus Vm sigma sub M equals 0.00286 times 100 gigapascals plus 0.9971 times 50 megapascals. Convert 100 gigapascals equals 100,000 megapascals. 0.00286 times 100,000 megapascals, approximately equals 286 megapascals. 0.9971 times 50 megapascals, approximately equals 49.9 megapascals. Sigma sub C approximately equals 286 plus 49.9, approximately equals 336 megapascals. Thus, adding just 0.5 weight% carbon nanotubes theoretically raises the composite strength from 50 megapascals to about 336 megapascals, illustrating the impressive reinforcement capability.